Right, let's look a little bit at the homework problems. And some of these homework problems include a difficulty that we have not really addressed in the lecture yet, and that's why I postponed it to the homeworks. That is going back and forth between spoken word and between English sentences and formal logic. And it's not always as simple as it looks like. So I want to do a few problems. I'm not going to do all of this, so I'm going to do 9D. So, okay, I assigned a few more from both sections, but let's do 9D. So 9D was the expression. We had these two. We have two predicates. The X runs over, the domain is the students in our school. And the two predicates are X speaks Russian and X knows C++. And so the statement that we want to write is no student can speak Russian or knows C++. Okay, so if we write it this way, we could try to do this like word by word. And I'm going to show you that is dangerous. So let's see what we could do. Say no student. That means it's not true that for all students can speak Russian, PX or QX. So that's my solution. Question mark. Is this the solution? How can we figure out that this is exactly what the original statement says? Well, and this is a point that I hope to make with this here, is that when we use formal logic, certain things are much harder for us to understand, especially when dealing with quantifiers, is also the negation of, when we use negation. Because negation, remember, behaves kind of weird, strange, right? I remind you of the De Morgan laws. The negation of a universal becomes existential, the inversion of a disjunction becomes a conjunction. So things do change when depending on where the negation is. Now, whereas in formal logic, it is simply from left to right. There is no discussion. This is how a sentence, the formal statements are built up. In English, although we write from left to right, we can move things around, right? So no student can speak Russian or no C++, but there are other ways perhaps that you can say that. For instance, I could say, neither Russian or C++ do any student speak. Perhaps I say the same, perhaps I'm not. Okay, so it is very difficult to analyze actually exactly what we say if we leave it in this way. The point I want to bring through is here that we need to, and that's what practice of the exercise and homework problems also are, is write this sentence so that the negation only applies to the predicates, because we very well know the negation of speaks Russian, namely doesn't speak Russian. Okay, so I'm going to do this using the Morgan laws. So remember, if this not, the not has to go all the way there and all the way there. How does it go? It's in several steps. And the first step is to bring it inside here, but that means that we have to flip. So this is the Morgan law, right? So the Morgan law for quantifiers, but I'm just going to write the Morgan. And then we have the negation of this whole thing. So better safe is to put the whole thing between parentheses. Now, it's still not in front of each predicate, because this expression here is still a compound propositional expression, okay? Or predicate expression. I should be more careful because there are actually X's on the predicates, but these are predicates, not propositions. Yet, so there is another De Morgan law. That's the one for conjunctions and disjunctions. It says, okay, if you do that, bring it inside, you have to flip the and or. So it is not PX or not QX. And I claim now that although perhaps a little bit more awkward to say it in English, it's much easier to understand its meaning. Let's see. There is a student that does not speak Russian or that does not know C++. Now, is that the same content as no student at your school can speak Russian or know C++? No. That statement says there is nobody like that. Here I'm saying there's just one guy that's not like that. Perhaps more, but the only thing I'm really claiming is there's one guy that doesn't speak, or neither one, so to speak. So conclusion, that this is not correct. Not what we want. Okay, so let's scrap it out. So what is then? How do we? So if we cannot just literally follow the English sentence, we have to analyze a little bit better what we're saying. So what we are saying is no student. When we say that, we say for all students they cannot speak Russian or know C++. That's the same thing. As I said, in English we can say, make again, reformulate our sentence, right? So you could, I'm telling you, no student can speak Russian or no C++. And you say, what did you say? Can you repeat this? And I repeat it one more time, and you said, sorry, can you phrase this differently because I don't know exactly what you mean? And then I would say, what I mean to say is that every student does not speak Russian or knows C++. Okay, so what is it then I'm saying? That for every, let me do it in black again. For all x, it's not true. Every student, he either he doesn't know px or he doesn't know C++. So for every student, it's not the case that he knows Russian or he speaks C++. For instance, for us to convey this better, we would say there is no student that doesn't speak Russian or C++. Like we don't double the verb, for instance, in this case. Now, again, as it's written here formally, so let me pronounce it as it's formally written. For every student, it's not the case that he speaks Russian or knows C++. The negation in front of that or is very confusing, and in fact, very many people in their arguments interpret this wrongly, or can use this to deliberately lead you on a false way. So, and to properly understand this, we should apply the Morgan law again to what we're saying here. The Morgan law here. So this means for all x, that doesn't apply to the quantifier now. For all x, is notice that I once in a while sometimes put parentheses around my quantifier to just make it more legible. It's not necessary, but I often do this because that's some textbooks do it that way. Okay, but here, so the quantifier the negation goes to both predicates, but remember the main thing of the Morgan law is that this flips into this, an or into an and. Let's now read again. For every student, he does not know Russian and he doesn't know C++. Let's go to the original statement. No student can speak Russian or knows C++. It feels like this is what the guy was trying to say. Okay. Now, I want to one more time point out how misleading English is, because I'm saying this is probably what he meant. But literally, because another thing that we could have done is, if you take the fact here that we have the for all x, but if we now, this or here, where is there, he says an or, and I actually have to write an and. That is because his no is actually negates this or. In other words, he is actually writing exactly what I said here, but this, as I said, is in English very misleading, right? Because as much, so suppose somebody would say no student can speak Russian and no C++. Well, he might say this, if it's not very bright, meaning exactly this, but he would say it wrong because he would use an and. If he would put an and here, that means the and would here, so after taking negation, it becomes an or. So the meaning changes, although it might have been the intention. So that's of course a different thing, what somebody intends and what somebody says. But now we go on what has been said. And this, as far as we can tell, corresponds to this statement. Okay, so just want to point out that there is a reason why we need formal logic, but formal logic is not easy to read. And therefore there is a reason why we have logical equivalences such as the Morgan law. Okay, and that the next problem that I want to look at is 33a. that I gave, right? 33a. So here we have again some old dogs can learn new tricks. Okay, so let's be the two predicates old x. That means the dog is old. X are just going to be old dogs. Okay, x, the domain is the dogs, and then the other predicate is new tricks. So new tricks x means that's a dog that knows new tricks, whatever that means. It's a saying, right? But okay. Okay, so some old dogs can learn new tricks. Here is what I would think. Let's think about what you probably, the first thing pops in mind is, okay, there is an old dog that knows new tricks, right? Some old dogs can do tricks. That means there is an old dog and he knows new tricks. Okay. Now we have to think, is this actually really what the sentence says? Okay, some old dogs can learn new tricks. And here I'm saying there is an old dog that is old and knows new tricks. Okay, so what can we think about this? Well, okay, it seems like we think this sounds correct, right? What we can now do, and that's actually what the question actually asks, is take the negation of this and then see what the statement says, and does it feel as the negation of the original statement? Okay, so this was, if you want, step 1. Step 2 was write the negation of this thing. It's not true that there is an x, old x, and new tricks. I'm going to leave it like this, okay, new tricks. That's just formally, right? Just the negation of a statement is just putting the not in front of it, okay? But as we said, this is not legible, so we're gonna make this into logically equivalent statements by moving this this negation all the way to these two predicates, because we understand the negations. The negation of an old dog is being a new dog, a young dog, and this means knowing new tricks means don't know new tricks, just do the same thing, same old. Okay, all right. So the first step, of course, is to bring it through this here. That's the Morgan law for quantifiers. That means that becomes a universal quantifier, not old x and new tricks x. Okay, but this is still dubious, not clear for us to understand, because the negation of an and is, we want to work this out completely using the other Morgan law. So this would be not old x, and of course what changes is the and becomes an or, not new tricks. Okay, let's now step 4. Let's read this. And this says for every dog. I'm not going to try to make a nice sentence. I'm just going to say it in an awkward way, perhaps. But for every dog, it's not old. It's not old, or it does not know new tricks. So it's not old. Let's make that even a little bit easier. Say it's young, or it does not know new tricks. Okay, that sounds the negation of what we're saying. Some old dogs can learn new tricks. This says every dog, it's young, or it does not new tricks. That seems to be a negation, right? Because it is true that if you're an old dog, what this says is there are some old dogs, not all of them, but some of them can learn new tricks. Okay? So from the negation, we see that our original is kind of what we intended. But as I said, this is not always so obvious. And So I don't know, I want to do one more perhaps. I didn't assign it, but let me do one more. There is no dog that can talk. Let's do that one. So this is 33D. There is no dog that can talk. So let's break. TX is the predicate that the dog can talk. So there is no dog. It's not true that there is a dog, X, so that he talks. Now I'm trying just to literally follow the sentence. As I said, it's dangerous sometimes, but let's see. There is no dog that can talk. It's not true that there is a dog that can talk. That seems to be what we want to say. So that was step one, right? Now let's take the negation of this. Okay, that was the next question. Let's take negation. That means we put a negation. There is an X, TX. Put a lot of parentheses so that we know what we're doing. The first thing is what happens here with these negations. Remember, the double of a negation is truth, right? That is one of these logical equivalences. Remind you, this is logically equivalent with that. Not is the same as just the property itself. Again, English sometimes, and especially wrong English, what we also call the double negation. People say they use double negation I'm not going to eat, what is it? I'm not going to, well, okay, I don't want to do this double negation. Just look at, examples of double negation. Okay, so that means here that logically equivalent, so I have to now make this logically equivalent. This is logically equivalent to there is an X, TX. The double negation disappears. And this is now in its simplest form. We don't need to do anything anymore. There's no not anymore. Okay, as I hope I made clear now or brought to the fore is that negations can be very difficult to understand how they work. That's why people make mistakes against double negations and so on. So let's see. This, what does this now say? In there is a dog that can talk. And it is clearly the opposite of what I was saying, right? I was saying there is no dog that can talk, and here I'm saying there is a dog that can talk. Okay. A dog that can talk. Well, I'll write here. Okay, sorry, it's a little bit late if you see from the time. Okay, let's do 933E. There is no one in this class who knows French and Russian. So again, X is students in this class. F of X is X knows French and what's the other language? Sorry, and Russian. Okay, X. So X speaks Russian. This was French. Personne qui parle français et okay, nagovori по-русски, but that's not so. I'm not so good in my Russian. It's very, very rusty. Sorry for the Russian speakers. Okay, so the statement is there is no one in this class who knows French and Russian. This is very similar to the first problem. So let's see how we solved it. At that time we said, okay, for everyone, it's not the case that they speak French. Where is it? There's no one in this class who knows French and Russian. Now notice that in the original sentence there is an and there, right? It's to the question that we did here, 9D, we had an or. No student can speak Russian or no speaker plus. Here is no student, it's basically the same sentence, no student knows French and Russian. So this means, if we think about this, means some speak French, some speak Russian, but there's nobody that speaks both, right? Like I was trying to do it, but I couldn't, so I'm an example of that. Okay, so is this what it should be? Well, okay, what the question asks is to take the negation of this. So let's follow these instructions. So we take the negation of this. So not for all x, not fx and rx. Okay. So now by the Morgan law, this is logically equivalent to, well, we bring the not inside, that becomes there is an x, not, right? This not has now moved there. Fx and Rx. So that's logically equivalent with, again, using this formula. There is an x, Fx and Rx. So going back, what was the statement? There's no one in this class who knows French and Russian. What is this statement now? If I would read this from, there is a student, there is a student who speaks French and Russian. And that's exactly the opposite of the negation of what this previous statement says. So we were correct in that. Okay? Now, again, this is logically equivalent. That was not a question, but let's work it out. This is logically equivalent to this for all x, not fx or not rx. Sorry, something weird happened there with my not or not rx. So logically equivalent, the original statement, there's no one in this class who knows French and Russian is for all x, they don't know French or they don't know Russian. Okay, so at least one of the two must be true, and that is exactly what we're trying to say. So you see, again, in natural language we use and, but if you actually work it out, there's an or here. And again, many times some people might want to say this, and instead of an and, they use an or. Okay, go on. Moving on. So I want to do also, now I'm going to go a little bit quicker now that I explained the pitfalls of these number 31 of 1.5. 31. Express each of the negations. I'm going to do only 31D, we said that we're going to do. So the negation of, I'm putting the negation already, and let's write down what the original statement was. For all x, there is a y, pxy implies qxy. Okay, so we have two quantifiers now, two variables, x and y. Okay, and it's kind of rather easy to go through all this thing, right? Remember, each time we go through a quantifier, we flip the quantifier. I'll do it in 2 steps. For all x. Oh, no, we flipped the quantifier, I said, and I didn't do that. So there is an x. It's not true that there is a y. Pxy implies qxy. And go bring this not again one further. There is an x, so that's for all y, not pxy, then qxy. Now, what about the negation of this implication? Right, that is some of the rules that we learned already. We learned that in 1.4 or 1.3, sorry, 1.3. And I remind you that one way to remember this, because you can just look up the formula, of course, but one way to remember is this. When was an implication false? Right? It was false exactly when the P was true and Q was false. So an implication is not true means exactly this. This is logically equivalent. Remember, we can replace any part of a formula by a logically equivalent formula. That is the rules of inference that we will talk about more in the next section. But here, so this means we can replace this by not pxy and not qy. Negation of an implication is, so what I'm saying is that this is logically equivalent to this. Sorry, I made a mistake. Pxy and not qxy, right? P and not q. I repeat, when is an implication false? If P is true and Q is false. That is a way to remember how this works, okay? So, okay, so this is now the statement in its simplest form where we have only negations referring to the at the predicates. There is an xy for all y's, pxy holds, and not qxy, okay? That was 35D, and then the other one, no, 31D, and the other one I wanted to do was, let's see, the other ones I'm going to leave from 31. What was the next number? 37. Number 37. Again, we have these English phrases. Every student in this class has taken exactly 2 mathematics classes at this school. Oh, no, this is not the one. I said B, right? Someone has visited every country in the world except Libya. Okay? So, there is a student X, so that he has, X has, for all countries, for all C, VXC. So, let me say what is this. We have to set up things, right? Unfortunately, the question has not done that. If I would ask this on a quest, I would set up these things for you. So let me set it up for you here. So we need predicates, okay? Again, X will be students in the class. So that's not the issue here. We know that's the domain. So what do we need? We are talking about visiting a country. So VXY means X visited country Y. So X is students in the class, Y are countries in the world. Okay? Country Y. Okay? So that's another thing. When we have variables, they can run over different domains. Every variable has its own domain. So here is a very good example of that, and that's very typical, right? That we have that we're talking about the grades of a student in every class. So if you would make for every student in every discrete mathematics class, every grade or something, like we want to make statements about that. Each of these variables talking about a different object, students, grades, classes, etc. Okay, so VXY is the statement X, student X visited country Y. Okay. 37b says, someone has visited every country in the world except Libya. Now the except one. So let's just try to say there is a student in this class. Sorry, I'm reading wrong percent. Someone has visited every country. Let's do this. For what is that? There is some X. And now what should we do with the Y's? Well, it's all countries he visited. So this is a statement. There is a student who visited, let me say it in words. There is a student who visited every country in the world. Now that's not what we want. We want to say there is a student that has visited every country in the world except Libya, because of, at the time, Gaddafi didn't let him come inside. Now there are a lot of countries in the world, so I doubt that there is actually one single person that has ever been able to visit every country in the world, but you never know. Okay, there is an X for all Y for XY, but that's not correct because we don't have the exclusion of Libya. How do we do that? Well, we say that 2 for all XY. Either Y, if Y is not Libya, then X must have visited it. So we can use this in if then. Right? So I'm claiming this is a solution. Let's do this. There is a student, so that for every country, if that country is not Libya, then he has visited it. Okay? So you would say, why not? So yeah, let's try another one. Why not say this? Is this correct? No, this says Y is not Libya and he visited XY. So let's see, why is this not true? For all, remember, when is an n true? An n is true when for and conjunction to be true, both have to be true. So if I say something like that, I'm saying it has to be an extra for all where y is not Libya. That's not true, because there is a country called Libya. And so this, forget about this part. This sentence, let me circle it in blue perhaps. This sentence only, sorry, this statement only, there is an x for all y is not Libya, is not, what I'm trying to say, is not true. Now, of course, granted, there is an x here, that it is a predicate. But this predicate can never be true, because it's a predicate, the predicate says for all where y is not Libya. Right? If we forget about the variable x. As far as the y is concerned, it says for all countries, the country is not equal to Libya. That's not the case, because there's a country called Libya. So this part is already false, and we know an and can never be true if at least one of them is already false. So this is therefore not, well, I want to do it in different color. This is therefore incorrect. Okay? And this is something that's weird. We feel that there should be an and, well, because somehow someone has visited country in the world except Libya. It seems like we're putting these two things next to each other. So it looks like a concatenation or some sort, and therefore we want to put an and here. So that is something you have to be very, very careful about. Okay. Yeah, which number 37b? Yeah, let's leave it like that. Some of these are getting really awkward. I wanted to only give you this ones only, right? Okay, that's enough for now.